So today we are going to learn about divisibility of integers. This is one of the first chapters that we learn when starting out number theory. Now, if you are starting to prepare for any Olympiads like Regional Mathematical Olympiad or INMO, RMO, INMO, and maybe entrance exams like ISI and CMI, or in general number theory, this is the first chapter that you're going to learn. So, in this chapter, what we are going to do is we are going to learn the basics of divisibility, how this works in terms of number theory. We are not really going to look at how a number is divisible by 5 or 4 or 7. That is divisibility of integers indeed, but that is just a corollary of what we are going to learn. So we are going to look at more interesting problems at hand and then do a couple of examples to sharpen our skills. And of course, those problems will be like Olympiad style. So the only important thing in this entire chapter is this result. If A divides B, this would imply that B is equal to A into C, where C is just another integer. And this would imply that A divides B. We can give a few examples here. Let's say 2 divides 4. And this is true because we can write 4 as 2 into some other integer 2, right? This would imply 2 divides 4. Similarly, you can also see that 1 divides 15. This is true again because 15 is 1 into 15. So whenever you can write B equals to A into C, it would always imply that C divides B and A divides B, both of them basically, because they are the factors of B. So this is the basic definition, but this basic definition is going to take us a long way in solving problems, as you shall see. So we should establish some common results which could be based on common sense, in fact, because this result A divides B and B divides C. So what happens if we have three integers A, B, C such that A divides B and B divides C? What can we conclude from this? Can we conclude that A divides C? And if we can we prove it? That is the question. So obviously you can again take examples of this. Like let's say 2 divides 6 and 6 divides 12. Well, we can see that yes, 2 divides 12. But how do you prove it algebraically? And when I say algebraically, you have this one identity at hand. This is what you're going to use always. So from the first relationship, we can say that B is equal to A into C1. Let's take P1 because C is already used. So A into P1, where P1 is an integer. Similarly, let's take C equals to B into P2, where P2 is also some integer because B divides C. Now from this too, we can establish the following. Since C is equals to B into P2 and B is equals to A into P1, we substitute the value of B here and we get this value as A into P1 times P2. Since P1 and P2 are both integers, then P1 into P2, which is the product of those two integers, should also be an integer, right? And since C is equal to A times some integer, we can conclude that A divides C. This is called the transitive property of divisibility. So these basic properties can always be established by using this basic rule of A divides B, then B equals to AC. And you should use it more often whenever you get any divisibility problem. And we shall see how this easily helps us do the problems that we're about to do, which are taken from past Olympiads and good books from number theory, good exercises basically. So they're neither hard nor easy, but they lie on a moderate level, I would say. Okay, so let's get on to one such problem. Find all integers n such that n plus 1 divides n square plus 1. So we have to find all such integers n. So that can be basically positive or negative such that it satisfies the condition that n plus 1 is a factor of n square plus 1 if stated otherwise. Well, one approach, as we have learned earlier, is this that we can always write from the definition n square plus 1 is equal to k times n plus 1, where k is nothing but some integer. But how does that help us finding n? Well, remember one thing, whenever you can form an equation like this, where the n square n is basically an integer, always remember that this is a quadratic equation, and that means it can be solved for two values. If you arrange in terms of an quadratic equation, you get this: n square minus kn plus 1 minus k equals to 0. And since this equation is an quadratic equation, it has two values. It also has a discriminant called capital D, if you remember from the quadratic formula, which was nothing but b square minus 4ac. And the root d term is present in the solution. Since the solution is nothing but solving for n, which is an integer, the root d term, this root d term that appears inside the solution, must also be an integer. Because if it is not, then n becomes a radical, right? It becomes a surd. So if root d is an integer, that means d must be some perfect square. That is b square minus 4ac from this equation must be a perfect square, right? So what is b square? K square minus 4 times 1 minus k times 1. Or in other words, k square plus 4k minus 4. This must be an perfect square. That is what the problem states. Now you can try and solve it, but I would not suggest this method basically. But this is a very useful method, and when the nothing is working, this is the only method you have to go to. The method we are going to use is something different and a little bit clever actually. Remember that if A divides P and A divides Q, then A will divide any linear combination of P and Q. So any alpha P plus beta Q, or even any powers of them. So basically, you can even write P square or P cube here, where alpha and beta are obviously integers. This is evident from the basic fact of the definitions, and you can try and prove it. So we are going to try and utilize that. So since n plus 1 divides n square plus 1, and also we know that n plus 1 must divide n plus 1 whole into n minus 1, because this is an expression which has n plus 1 inside it already, so obviously n plus 1 should divide this whole thing. But if you factorize this, it is in the formula of a plus b into a minus b, which gives you n square minus 1. So n plus 1 divides n square minus 1 is also another equation that we got just from the fact that the expression is n plus 1, right? Now, since n plus 1 divides this and n plus 1 divides this as well, n plus 1 will also divide the subtraction of these two expressions, right? So n plus 1 will also divide n square plus 1 minus of n square minus 1. You can also think of it this way, that since both of these terms are divisible by n plus 1, any combination of them is also divisible by n plus 1. But if you simplify this, this simply turns out to be 2. And we get the very basic equation n plus 1 divides 2. And from now on, you do not need to do anything, because there are only a handful of integers which can divide 2, which are the factors of 2, right? What are the factors of 2? The factors of 2 are simply plus minus 1 and plus minus 2. So n plus 1 must be equal to these in some order. So let's try and equate that. So let's say n plus 1 is equals to plus minus 1 and plus minus 2. If you solve for n, the values you get, so if n plus 1 is plus 1, n becomes 0. If n plus 1 is minus 1, n becomes minus 2. Similarly, n plus 1 is 2, n becomes 1. And if it is minus 2, n becomes minus 3. So these are the four values of n which satisfy our given problem, and we have solved the problem. We have solved this problem completely. So you can understand how this method was proven more beneficial than this one. But as I am stating repeatedly, this is the better of the two methods in problems which are way tougher than this. But yeah, you should also look to exploit to try and subtract different things from the right hand side of the divisibility. In terms of expressions, try and subtract expressions which are factors of the divisor, so as to reduce the right hand side, like I did here, like n square plus 1, and I immediately realized that n square minus 1 was a factor of n plus 1. Okay, so I hope this problem was clear. Let's get on to another problem, something of the similar type. So you can try this first and then look at the video. Actually, that would be helpful because you have just learned how to tackle this kind of problems. Granted, this is a different problem and it's a bit more complicated probably because of the cubes and all, but still. Okay, let's begin. So what I'm going to do first is I'm going to simplify this. So let's say x equals to n minus 3, because I do not really like the look of it. And since x is n minus 3, this problem simply translates into x, and n becomes x plus 3 whole cube minus 3. Okay. Now, what this statement means is that x divides. Now, if you were to expand this, you would simply get this x cube plus 3 cube plus 3 into x into 3 whole into x plus 3 minus 3. Notice that x divides x cube and x also divides this expression right here because both of them have an x in it, which means this directly implies that x divides 3 cube minus 3, right? So again, the same thing we learned in divisibility. If x divides a plus b, and you already know that x divides a, this would directly imply that x divides b, because you can simply subtract them. You can simply do it like this, a plus b minus a, right? Okay, so what is 3 cube minus 3? It's 27 minus 3, which is 24. And thus we have got our value. X is basically the factors of 24, which are plus minus 1, plus minus 2, plus minus 3, plus minus 4, plus minus 6, plus minus 8, plus minus 12, and plus minus 24. I think those are all. So if you equate the values of x to each of them and then try and solve for n, where n is basically 3 plus of that, you will get all the required values of x and n. And that completes the problem again. So these are basic divisibility problems. And these rules need to be followed when solving a particular question. So I hope both of these examples were clear to you, and the basic definition of divisibility as well. If there are any doubts, please let me know in the comment section. I will try my best to clarify them. And wait for the next video for the RMO 2024 series. And well, of course, this is valid for all years, regardless of the year. But right now, while recording, it is 2024. Okay, so thank you, and please subscribe the channel, and also maybe like the video if you really like this sums and the style of explanation. Thank you.